All right. So first problem you consider a four pole 1500 rpm DC generator has a lap wound armature. Four pole 1500 rpm DC generator has a lap wound armature winding having 32 slots and 8 conductors per slot. If the flux per pole is 0.04, calculate the EMF induced in the armature. What would be the EMF induced if the winding is wave connect? So this is a given problem. So initially you have been given with a lap wound machine, right? And you have been asked to find out the induced EMF for a lap wound machine, right? So that will be the first objective, and the second objective going to be the EMF induced in a wave wound machine. All right. So first, let us look at first part. So induced EMF, okay, induced EMF. In DC generator can be given as E is equal to pi Z NP divided by 60A. All right. So for a lap wound machine, here itself we can create the two cases. For a lap wound machine, we have P is equal to J. And P is equal to A, and that is 4, right? Because number of poles is equal to number of armature parts, and number of poles being given as 4. All right. And then you don't know the conductors, right? Indirect detail has been given. That is, conductor per slot is 8, and number of slots are 30. So therefore, you can just cross multiply to find out conductors. So conductors Z is equal to 8 into slots. That is 8 into, and how many slots? 32 slots. So 8 into 32, 256. 256. Now you can find out EMF. So E is equal to 5, 0.04. Z 256. Again, speed of operation 1500. P is equal to 4 divided by 60 into A. A is equal to P, that is also 4. So basically, P and A gets cancelled off, due to which you will get the induced EMF as 256 volts. 256 volts. Now let us consider case B. So case 1 is dealt with. Case B. So in case B, what is that you are seeing? You are seeing that you'll have to recalculate the EMF if the winding were connected to the wave manner. So for wave winding, number of armature parts are always two. Only two armature paths are used in wave winding. So due to which EMF E becomes, formula remains same. Phi is 0.04, Z 256, speed 1500, and poles 4 divided by 60 into A is equal to. So due to which the EMF becomes 512 volts. This is what I was saying in the beginning. If you go for a lap wound machine, you will be able to generate lesser voltage, but you will be able to handle more, larger currents, right? That's because you have more number of parallel paths. So a larger current can be safely distributed into the parallel paths. On the other hand, in wave winding, if you look at, you will get the voltage is almost twice the value of the lap winding. So wave winding is ideal for high voltage, low current applications, and lap winding is ideal for low voltage, high current applications. All right. So that's your first problem. Let us look at problem number 2. All right. Take down. The induced EMF in a DC generator running at 1000 RPM, 1500 RPM is 500 volts. So, induced EMF is 500 volts when the generator is running at 1500 RPM. Full stop. Calculate the EMF induced. Calculate the EMF induced when it runs at 1000 RPM at n is equal to 1000 RPM. Calculate the EMF induced when it runs at 1000 RPM. The flux remaining the same. So flux is same. Then part B, find the percentage increase in flux so that the induced EMF at 1200 RPM is 600 volt. So percentage change in flux so that the induced EMF at 1200 RPM is 600 volt. Right. So you have been given with two cases. The first case is find the EMF of the generator when the generator is running at 1000 RPM, assuming that flux is remaining the same. In the second case, they are asking us to find out the percentage increase in flux in order to generate an EMF of 600 volts at a speed of 1000 RPM. Alright, so this particular problem needs to be solved very, very systematically. So first let us consider part A. Part A. So in part A, as you can clearly observe that you are supposed to consider flux as constant. So let us write flux is assumed to be constant. Alright. And you have one EMF which is 500. And you have one speed value which is 1500 RPM. And you need to determine different EMF at different speed. So we shall take let E1 is equal to 500 volts and N1 is equal to 1500 RPM. Right? We need to distinguish the two EMFs as well as the two speeds. Similarly, let us take E2, which needs to be found, and N2, which is actually given, which is 1000 RPM. Okay, fine. So this is the given data. I've just written the given data. Of course, with two different subscript we have used. Subscript 1 and subscript 2 to distinguish the two EMFs and the two speeds, right? The next step is to write down the EMF equation. So we know that the EMF induced in a DC generator can be given as E is equal to pi Z NP divided by 68. Okay. And we have been asked to take flux as constant. So you can take E, okay, flux as constant, right? So you can basically take these terms as constant. Let me highlight those terms. So the terms which are sitting within the red color are basically the constants. Force is constant, number of conductors, and flux is also constant. So basically, the constant in this equation is pi Z P divided by 68. So you can write E is equal to some K times N. So E is equal to some K times N, where K is a constant. And what is the value of K? K is basically pi Z P divided by 68. So therefore, you can write E1 is equal to K into N, and E2 is equal to K into N2. K remains same because the same DC generator you are considering, right? In both the cases, phi remains same, number of conductors cannot change, poles cannot change, and 68 cannot change. So on that note, you can take K as constant. Okay. So let's take this as equation 1 and this as equation 2. You divide the two equations so that you get E1 by E2 is equal to, what you get when you divide the right hand side terms? K by K gets cancelled, N1 by N2 you will get. So what is that you want? You want E2, right? So E2 is basically N2 by N1 into E1, and N2 is 1000 divided by N1 is 1500 into E1. E1 is 500. Right. So that will give you E2 as 333 volts. So that is your first part of the problem. All right. Now let us try to solve the second part of the problem. So in the second part, what is that we should find? We should find the percentage increment in flux in order to get a voltage of 600 volts at a speed of 1500 R. Now, in case part B, we should understand the fact that flux is not constant. All right, so this is very, very important. Flux is not constant. And on what basis I am saying this? Flux is not constant. The question itself says, right? You need to find out the change in flux. Change in flux means flux is obviously changing. Okay. Now, to handle this particular case, you have to do is you have to start with the fundamentals. That is, write down the EMF equation. E is equal to pi Z NP divided by 68. All right. Now, once again, you will have to identify the machine constants. Now, the question is, can you take phi as a constant? No, you can't take phi as constant, right? Because phi is variable. So, in case B, the constants are 68 and P, Z. Only these terms are constants. So, red color indicates that they are circuit constants. So, due to which, what you get now, you get E is equal to, okay, some K into phi into N. So, your EMF, E is basically K into phi into N. All right. So, therefore, you can write E1 is equal to K into phi 1 into N1, and E2 is equal to K into phi 2 into N. Once again, K remains same because it's the same machine. Let's say this is equation 1 and this is equation 2. So let's divide the two equations. So what do we have? E1 by E2 is equal to K phi 1 N1 divided by K phi 2 N2. So K gets cancelled. So you will have phi 1 into N1 divided by phi 2 into N2. So what you can do is, fluxes are not known, right? So let's keep the flux ratio on one side. So we have E1 by E2 into, that is cross multiplied, N2 by N1, which is equal to phi 1 by phi 2, right? So this is my main equation. Now with respect to this equation, I can proceed further, right? So what do I get? I get phi 1 by phi 2 is equal to E1 by E2. What is E1? The original EMF, phi 1. Divided by E2, the new EMF. In case 2, the new EMF is 600 into N2. What is N2? 1200 RPM. Divided by N1, 1500 RPM. So you can calculate that particular ratio. So phi 1 by phi 2, you will get it as 0.66. Right. .667. Okay, I'll continue here. So therefore, you can write down phi 2 as basically 1 by 0.667 times phi 1, or what is the reciprocal of 1 by 0.667? The reciprocal of 0.667 going to be 3 by 2. That's 1.5. So your flux value, the new flux value phi 2 is 1.5 times the old flux value. So therefore, change in flux. Therefore, change in flux, or rather, percentage change in flux can be given as phi 2 minus phi 1 divided by phi 1. That is new minus old divided by old. So that is, what is phi 2? Phi 2 is 1.5 minus phi 1 divided by phi 1. And that is equal to 1.5 minus phi 1 into 100. Okay. equal 100 because you are asking percentage change, right? So that is 0.551 divided by 51, 200. 51 gets changed, cancelled. So we will get change in flux as 50%. So you can write, therefore, percentage change in flux is 50%. In specific, the percentage increase in flux is 50%. So when your original flux phi1 is increased by 50%, the EMF can be changed to 600 volts. That is what you understand, or the conclusion what you can draw from this particular problem. Okay, so this is our problem number 2. Any doubts in this? So, such problems you can expect from EMF equation. All right. So now let us look at the problems which are based on KVL and KCL equation. All right. So let's start problem number 3. It says shunt generator has no load induced EMF of 150 volts. It's a shunt generator has no load induced EMF of 150 volts. So induced EMF at no load is 150. When it is loaded, the terminal voltage decreases to 140. The terminal voltage decreases to 140 when the generator is loaded. Okay. The armature resistance and field resistances are 0.2 and 100 ohm respectively. Find the load current. Find the load current. Ignore armature reaction drop. Ignore armature reaction drop. So, solution. Let's try to understand what kind of problem it is. So, in this particular problem, you see conductors, the flux value, etc., is not given. And to that matter, even speed is not given. So, that means to say it's a different problem. What you have been given with is the EMF value, which is 150 volts. The terminal voltage is given 140 volts. And the circuit resistances have been given. Armature reactance is 0.2 and shunt field resistance is 100 ohms. And you are supposed to find the load current. Now, you have been asked to neglect the armature reaction drop. So, in the solution, you can write ARD is 0. And there is no information about brush contact drops. So, since there is no information, let us assume it as 0. Alright. This is the first aspect of this problem. Now, what you can do, instead of writing straightforward equation, let me draw the equivalent circle. Okay, always, such problems needs to be solved with the help of equivalent circle. That creates a lot of clarity while solving the problem. Right? So equivalent circuit is construct. So this is A double A this is RA. RA is 0.2 ohm. And then you have the shunt field, right? And shunt field resistance is 100 ohm. This is shunt field current ISH. This is armature current IA. This is your load. And this is the terminal voltage. Minus plus, which is 140. And EG is given, right? So this is EG. This is IA drop. Okay, so what is EG? EG is 150. So that's all. That's a problem, right? So what you have to do is you have to find out IL. So let us mark IL. What is IL? IL is the load current. This is your IL. This is your IL. Research and this is your IL. So IL needs to be found. So you can apply KCL. So when you apply KCL, what is that you see? Incoming current at this node is equal to two outgoing currents. So your armature current IA is equal to ISH plus IA. And the load current IL is nothing but subtraction of IA and ISH. And ISH can be directly found. So ISH is nothing but voltage across the field winding. What is that voltage which is coming across the field winding? There's nothing but the terminal voltage. So terminal voltage by resistance. So it is 140 divided by, right, or 1.4 amps. So that's your ISH. And if you can calculate IA, you will be able to find out the load current IA. So how will you calculate IA? To calculate IA, you can apply the KVL. So apply KVL. In clockwise direction, CWD, clockwise direction. So what do you get? You get EG minus IARA, right? EG minus IARA, and then drop across this, which is nothing but 140 is equal to 0. I'm not considering brush drop and armature reaction drop, right? I'll write VD, and later let me substitute. Let me write VD. So you can rearrange this equation to get the value of IA. So IA is nothing but EG minus VD divided by R. So IA is equal to, what is EG? 150, VD 140 divided by RA. RA is 0.2. So it is basically N by 100. Right, so 100 by 2 is 50. So armature current is 50. Therefore, load current IL is equal to 50 minus ISH, which is 1.4. Right. So that is 48.6. .6. So that's your problem number 3. All right. So very simple problem. me solve one more. Problem number 4. Write down a 4-pole DC shunt generator with lap connected armature has field and armature resistances of 50 ohm and 0.1 ohm respectively. Field is RSH and RA is 0.1. If the generator supplies 60 100 volt 40 watt lamps, 60 100 volt 40 watt lamps, calculate the total armature current. Calculate the total armature current, comma, the current in each armature conductor and the generated EMF of the problem and the generated EMF. Take 1 volt per brush as contact drop. So brush contact drop is equal to 1 volt per brush. 1 volt per brush. Okay. Quite a big problem. Let's try to understand what are they trying to convey in this particular problem statement. DC shunt generator, pretty straightforward because it is given. The two resistors have been given, RSH and RA, right? And this particular generator is supplying 60, 100 volt, 40 watt lamps. So the lamp in this particular problem is consisting of this particular specification. So the generator is supplying 60 watts and the generator is supplying 60 lamps and each lamp is having a rating of 100 volt 40 watts. All right. So let's try to recreate the problem. This is how the load is connected, right? Parallel, correct? Parallel. This is your lamp. Let's say this is your switch. It doesn't matter. So this is your second lamp. And this is your switch. Alright. And this will go on. So this is your L1. This is your lamp 2. And this will go on till 60th lamp. This is your L6. Alright. So this is the load. This is how the load is connected to. In a nutshell, you can just call it as load. So this load is consisting of 60, 100 volt, 40 watt lamps. Now what you can do is you can find out lamp rating. So from the lamp rating, if you are able to find out the current drawn by one lamp, you will be able to find the load current. Let's say all these switches are closed. So let us take this current as IL1, this current as IL2, and this current as IL6 because there are 60 currents. So lamp rating, let us find. So what is it? Power rating P is equal to V into I. All right. So power is 40 watt and voltage rating is V. So I can be found as P divided by V. So it is 40 watt divided by 100 volts, right? So it's correct. 40 by 100. So 0.4 ampere. So each lamp is drawing 0.4 ampere. So this draws 0.4, this draws 0.4, and even this draws 0.4. So what is the total current drawn? So total current drawn, IL, is equal to number of lamps into current drawn by 1. Correct. Because as per KCL, IL is equal to IL1, IL2, IL3 until IL60. So what happens is that your IL becomes, how many lamps you have? 60, right? So it is 60 into 0.4. So it is 24. So your load is drawing a total current of 24 amperes from the supply. That's all we need to proceed further. So now you can, construct the equivalence of it. This is your generator. The field winding. This is your load. You see, such a big load we are just replacing with a small, tubular shaped object. So what is the load current drawn by this load? It is 24 amperes. And this is IL. And this is the terminal voltage. So what is the terminal voltage of lamp? 100 volts. So terminal voltage is 100 volts. And then you can write down RA. So RA is equal to 0.1. RSH is equal to 0. This is IA. This is ISH. Right. You know the voltage across the shunt field winding. What is that voltage? VT. And you know the resistance. So what you can find out, ISH you can find. So ISH is equal to voltage by resistance. Voltage is 100 divided by resistance is 50. 2 amps. You know IA, you know ISH. So you can find out IA because armature current is always load current plus shunt field current. So armature current IA is 2 plus 24 is 26. That is what you are supposed to find out. So first part you have found. That is armature current is 26. Done? Second part, what is that we are supposed to do? Current in each armature conductor. Let me write. Current in each armature conductor. Now, for this, you need to understand the type of winding which is being used. Now, which type of winding is used? Lap winding is used. In case of lap winding, number of parallel paths is equal to A is equal to P. And it's a P-pole machine, so P is equal to 4. So A is equal to. So basically, you will have 4 parallel paths. Four parallel paths. So this is your armature current, which is 26 amperes. So armature current gets in and gets divided into 4 parts, and it will come out as IA is equal to 26 amperes. And what is that you are supposed to find out? You are supposed to find out armature current in each armature conductor. That's all. So you are supposed to find out this current. Say, IA. IA is armature current, and capital A stands for parallel path. That is the current found in parallel path. So this is also IA, and equally distributed conductors in parallel path. So therefore, IA is equal to 26 divided by 4. Right, so that's about 6.5 amperes. 6.5 amperes. So each conductor, or rather each parallel path, is drawing about 6.5 amperes of current. All right. So that concludes part B. Coming back to part 3, very straightforward. Part 3. It's about finding out EMF by taking 1 volt per brush drop. Okay. So part 3. Yeah. So brush contact drop. Let me write in the beginning itself, right? So they are told take 1 volt per brush. So usually, we take pair of brushes, A and W. So for 1 brush it is 1 volt. For 2 brush it is 2 volt. So brush contact drop is 2 into 1 volt, which is 2 volt. Because we use 2 brushes, pair of brushes, right? So that's 2 volt. And armature reaction drop. Do we have any information of armature reaction drop? No information, hence 0. Hence you can find out the generated EMF Eg is equal to Vt plus IARA plus brush contact drop. So Eg is equal to terminal voltage 100 plus armature current is 26 into resistance of armature winding is 0.1 plus brush contact drop is 2 ohms. So basically 102, 104, 104.6 you should get. Okay. So Eg is 104.6. So that's about your part. And that concludes the problem. All right. So I have to solve problems on compound machine as well. So that I will take it in the next class. All right. So that's it for the day. I hope you have understood the problems.